We'll get started. Just an announcement, quiz 2 is uploaded. It is due next week on Tuesday, midnight. It's based on lecture 3 to 6, I think, yeah, 3 to 6. So please do review it. We're not, so the quiz 2 doesn't contain information on eigenvalues, eigenvectors, all the stuff that we're talking about now, but it contains information about the definitions of linear system and all the causality and all of that stuff that we talked about, uniqueness of solutions and so on. Okay, so last week we were talking about computation of exponential of AT, and what we talked about in the previous class is A is diagonalizable, T inverse AT equals to lambda, and in this case the in that case, there is an easy way to compute the expression for the exponential of AT. So exponential of AT equals to T times exponential of lambda T. So this one is very easy. Along the diagonal terms, you take the lambda and then you take e raised to lambda T along the diagonal terms, and then you multiply it by T, pre-multiply it by T, and post-multiply it by T inverse. You get the exponential of AT. Today, my goal is to cover two topics. I don't know whether we'll have the time to cover both of them or not, but the first part is when A is diagonalizable and lambda 1 to lambda n are complex. So that's the first part. I think this is going to be a small, very small discussion. And then the second part would be discussion on Jordan canonical form and matrix exponential. So when you were talking about signals and systems and feedback control systems in those classes, you are generally in this particular domain where lambda 1 to lambda n are complex. And generally speaking, in those cases, we didn't really care. I mean, there was no matrix to be matrix to diagonalize, but we did. But I think you guys would have seen. Or rather, when we talk about the Jordan canonical form and the matrix exponential, I'll tell you what the connection to the signals and systems and feedback control systems classes are. I know that's not a prerequisite for this class, but I'm pretty sure many of you might have taken it either when you were doing your undergrad somewhere else, or you might have seen it in some other signal processing class or some other controls class. Okay. So let's talk about the case where lambda 1 to lambda n are complex. So if any of you have taken feedback control systems in the past or signals and systems in the past, what happens when you have complex roots? What kind of behavior do you see in your impulse response or step response of the system? Anyone remembers?
You see an oscillation.
You see oscillations. And sometimes those oscillations are damped oscillations, so the oscillations die down and the system reaches some sort of steady state behavior. And in some cases, those exponentials amplify, and then the system reaches a point of instability in the sense that the amplitude of the system goes all the way to infinity. Okay, so generally speaking, when A is a real valued matrix, which means that all the elements of A is are real they are real numbers, then whenever you have a complex eigenvalue, then the conjugate of that eigenvalue is also an eigenvalue for that matrix A. So if A is Rn cross n and lambda in C is an eigenvalue with eigenvector u plus jv, I think I'm going to use w, not v. Okay, let me use u plus jw. Well, I'm going to confuse between w and omega, so let's use v. Then lambda bar is also an eigenvalue and u minus jv is an eigenvector. Okay, so this is a fact. We are not going to prove this fact, but it is true. And so now the question is, how do we think about matrix exponential in this case? You can certainly apply this formula where T would be a whole bunch of complex, it'll have complex entries. So this matrix will have complex entries, T inverse will have complex entries. This will have complex exponentials along the diagonal. But it will all work out. You will get the same expression that you will get while applying the approach that I'm going to take now. But I just want to show you that there are two different ways to reach the same conclusion. So one way is, it's okay if these are complex. I know how to take the complex exponential. This will be a complex matrix. This will be a complex matrix inverse. I can do all of that multiplication and I'll get the matrix exponential, which will be a real valued matrix. Even though everything here would be complex valued, this will turn out to be a real valued matrix. But let's do it in some other way, just because it's more instructive and it would probably be easier to understand that. And so let's think about it. I have A, so let me define lambda to be sigma plus j omega. So this is omega, not w. And so A u plus jv equal to sigma plus j omega u plus jv. So matrix times the eigenvector equals to eigenvalue times the eigenvector. I want to remind you j equals to square root of -1. Okay. This one is scalar, this one is scalar, this one is a vector, this one is a vector. Okay, so u v is in Rn, sigma omega is in R, and j is a complex value. What should we do? Let's try to expand terms on both the sides. So I have AU plus JAB equals to sigma u minus omega v plus j sigma v plus omega u. Okay, so this means AU equals to sigma u minus omega v, and AV equals to sigma v plus omega u. Any questions so far? Right, so these are all the real value terms, these are all the complex value terms. So I collected them together and I get this expression. Now my question to you is, what happens if I want to do this? So this is a matrix in Rn cross 2. This is a matrix in Rn cross n. So I have two columns. The first column is U, the second column is V. What do I get on this side? Let me write it down. Sigma Yeah, I think this is perfect. Okay, any questions so far? We're just doing massaging of the matrices. Anyone has any questions on this? Sounds reasonable. So I have n complex eigenvalues, and I have the dimension of the kernel space of A minus lambda I is the same as the multiplicity, algebraic multiplicity of lambda I, as a result of which A is diagonalizable. I have n unique eigenvectors corresponding to these eigenvalues. Some of these eigenvalues would be complex, in which case I will have the conjugate would also be an eigenvalue, and u minus jv would also be an eigenvector in those cases. So you will have like lambda 1 conjugate, lambda 2 conjugate, and so on. But you will have at most n eigenvalues. So lambda 2 would be lambda 1 conjugate, lambda 4 would be lambda 2 conjugate, and so on. And you will get n eigenvalues of the matrix A. And so after doing some massaging, I come to the conclusion that if I multiply A by u comma v, a matrix that is constructed of the real part of the eigenvector and the imaginary part of the eigenvector, I get the same matrix multiplied by this 2 cross 2 matrix. Okay. So let's define my matrix T as u1, v1, u2, v2, and I'm not going to write UNVN because that would violate the requirement that you could have at most n columns in this. So it would likely be UN over 2 VN over 2. Okay. So assuming that n is even, that would be the case. If n is odd, then you will have a real eigenvalue and you will have a potential real eigenvector towards the end. So I'm just going to assume that n is an even number. So the dimension of the matrix is n cross n. N is an even number. So this T is now in Rn cross n. It is also a fact that all of these eigenvectors, all of these vectors are going to be linearly independent of each other, as a result of which T would be an invertible matrix. And then what do I get if I multiply A by T? Sigma 1 omega 1 minus omega 1 sigma 1 and then 0 and then 0, and sigma 2 omega 2 minus omega 2 sigma 2. You will have a matrix that looks something like this. So it will be sigma 1 sigma 1 sigma 2 sigma 2 along the diagonal, and then off diagonal terms would be minus omega 1 minus omega 2 and so on. So now my question is, I want to take the matrix exponential of this. So if I move T on the other side, I will have T inverse AT is given by this matrix. So if I want to take the exponential of AT, I can pre-multiply by T inverse, I can post-multiply by T, and that will be exponential of this particular matrix. However, here that matrix was lambda T. Now here that lambda is no longer a diagonal matrix because you have some off diagonal terms in the matrix. So what should we do? How should we go about coming up with matrix exponential for this? Any idea? Let's think about it. Can I erase this side of the board? Any questions so far before I erase this side of the board? No? Okay, so let's say I have a matrix. What should I call that matrix? Let's call that matrix lambda. Although initially we were using lambda as a diagonal matrix, let's assume that lambda is an arbitrary matrix, but it's given by lambda 1 0 lambda 2. So this is a square matrix. This is a square matrix, but off diagonal diagonal terms are 0. Sorry, off diagonal terms are 0. So you have like one block of matrix 0, another block of 0, and then the matrix. I want to compute the exponential of lambda. This is identity plus lambda square over 2 factorial and so on. So I can write this as 0i So this identity can be broken into smaller identity matrices that are on the diagonal. I know that I'm making a leap of faith here. This identity matrix is of higher size, this identity matrix is of lower size, but I'm sure you can understand from the context what the size of these matrices are going to be. This would be lambda 1 0 0 lambda 2. What about lambda square? What is lambda square? If you do the math, you will realize that when you square the matrix, you will have square of the first diagonal term, square of the second diagonal term, but the off diagonal terms would remain 0 0. Are you all convinced of this expression? Have you done this before? Okay. So it will turn out that lambda raised to k would be lambda 1 raised to k 0 0 lambda 2 raised to k, proof by induction. You can establish this result by induction. Not a big deal. And what that implies is this is the same as exponential of lambda 1 0 0 exponential of lambda 2. And if you have multiple such blocks, lambda 1, lambda 2, lambda 3, lambda 4, and so on, you will have an appropriate exponential terms along the diagonal. Okay, so things are getting more complicated. So earlier we were looking purely at the diagonal matrix. So this one was exponential of lambda 1, which is a scalar, exponential of lambda 2, which is a scalar, and so on. Now each of this is a matrix, so now we have to compute the exponential. But instead of computing the exponential of a larger matrix, now I have to compute exponential of smaller matrices. Okay, so there is some simplification, not as much as we would have hoped, but definitely we know now that the off diagonal terms are going to be 0 when you do the exponential of this. And then along the diagonal, you still have to compute the matrix exponential. Perfect. Yes.
Is this equality asymptotic?
Sorry?
Is this equality asymptotic, like as k goes to infinity?
This will work for all k.
Okay.
And you are going to add up all of these k's here, right, in exponential term. Right? So yeah, this will just convert itself into exponential of the individual matrices. Does that make sense? Remember, this is going to be summation 1 over k factorial lambda 1 raised to k lambda 2 raised to k. K goes from 0 to infinity. Right? Because of this reason. And so each of this term will get added with 1 over k factorial, and that will give you the exponential of lambda 1. And the same thing here will give you exponential of lambda 2. Yes, please.
Can k be like not an integer or a negative number?
Not in this particular case, because exponential expansion contains only only the non-negative integer. So okay. Yeah, it's, we are not really doing gamma functions and all that stuff that people tend to study in calculus, so we don't have to do all of that here. So it's going to be only non-negative integers in this class. Okay. Perfect. So we have this complicated problem. We are sort of peeling the layers of this complicated problem and trying to solve each of that peel. So once I saw this matrix, which has like off diagonal elements are 0, diagonal elements are a bunch of matrices. So at least I've been able to simplify, and I can apply the same technique, and if I have like n such matrices, then the exponential of matrix 1, exponential of matrix 2, exponential of matrix 3, and so on will come on the diagonal of this matrix. So there is some simplification, but now the problem right now is I still need to figure out what is exponential of sigma omega minus omega sigma. So now that's the second problem. So initially my problem was I need to solve this complicated exponential thing. So I converted into this. Now I have to compute each of these exponential terms, exponential of this matrix, exponential of this matrix, and so on. I want you to spend some time, maybe a minute or two, look at your notes from the previous lecture and try and figure out how do we solve this problem. Okay, now this is problem number 2. How can I compute the matrix exponential of this matrix? So while you think about it, I'm going to erase this side of the board. So this is my step 1. Now step 2 is I need to compute exponential of lambda I, which is exponential of sigma I omega I minus omega I sigma I. I have an idea. The idea is that in the previous class we learnt about this cool identity that exponential a plus b equals to exponential a times exponential b when ab equals to ba. Okay, when AB equals to BA, then I can convert exponential of A plus B into exponential of A and exponential of B. What can I write this as? Can someone help me decompose this matrix into two matrices, sum of two matrices that commute? Yes, please.
If you break it into one matrix that's just the real part, and one matrix that's just the imaginary part, and take what you need for both diagonal.
Is this what you are thinking?
Yes.
So I have an identity matrix multiplied by a scalar, that's fine, because it's a scalar, I don't care about it. And then multiplied by some other matrix. It's not an identity matrix, it's an off-diagonal matrix. That's fine. But does that satisfy this condition? So A is sigma times identity, B is some matrix. Is that equal to B times sigma times identity? So remember, sigma is a scalar, so scalar doesn't matter. Scalar commutes with all matrices. So you have identity times this omega matrix equals to omega times identity matrix. So identity commutes with all matrices. So I can actually apply this this result from the previous class to compute the exponential here. So what is exponential of lambda I? This is exponential of sigma I times exponential of 0 omega I minus omega I 0. So I'm going to apply that identity we talked about in the previous class, and I can write this matrix exponential in this particular fashion. This one is actually very easy because we have talked about it so many times already. This is e raised to exponential of sigma I 0 0 exponential of sigma I. What about this exponential? So it turns out this exponential is equal to cos omega I sin omega I minus sin omega I cos omega I. Okay, why should this be the case? So let's think about it. Why should exponential of this be equal to this? Okay, I'll give you the reason. I'm going to compute the exponential term for this particular matrix now, and it will turn out that as you keep adding these terms, as you keep adding this exponent, the terms in the exponential, you will get a power series expansion of cos, sine, minus sine and cos. And that would lead us to conclude that this exponential is actually equal to this particular value. So let's look at 0 omega I minus omega I 0 square. What is this equal to? You don't have to write it down, but you can certainly help. And so on. So what do I get as exponential of 0 1 0 0 1 0 So this is what we get. Okay, so what we have is the first term is 1 minus omega I square over 2 factorial plus omega I raised to 4 over 4 factorial and so on. That's the series expansion of cos omega I. This term would be series expansion of sine omega I. This term would be minus sine omega I. This term would be cos omega I. That gives us the matrix exponential for this. So this is step 3. Step 3 is recognizing that this is the matrix exponential of this term. Okay, so let's bring all the 3 steps together. I have constructed but can I erase this side of the board? Okay, so let me write it down here, the final answer. So this is exponential sigma I times cos omega I. This is exponential sigma I times sine omega I. Exponential sigma I now I can erase this part. So T inverse exponential A T equals to exponential lambda 1 0 0 exponential lambda 2 exponential lambda n over 2. This is a real matrix. This is a real matrix. This is a real matrix. And this is a real matrix. Okay, so this is slightly different from what we did earlier. In the earlier case, if you had a diagonalizable matrices, so you can take all the matrix exponential, the complex exponential, and you can still get the same result. This will give you exactly the same result for matrix exponential, but it's just that you're doing it completely in the real domain and you're not going into complex numbers at all. Just a bit of mental math is needed in order to get to this particular expression. The reason why we did this was not because we don't know how to do the matrix exponential using the previous approach, but to introduce all of these new techniques that we just introduced, which is if you have a bunch of blocks along the diagonal and you want to take the matrix exponential, then it's the block diagonal structure of the matrix exponential of each diagonal element. And also this exponential expansion of this particular matrix. Okay, any questions so far? Perfect. So far what we have done is, if the matrix is diagonalizable, which means that if the dimension of the sum of dimension of the eigenspaces is equal to n, in that case the matrix A is diagonalizable. You collect all the eigenvectors in the matrix T and then you do T inverse exponential of AT, you get some desirable structure, and then you can post multiply it by T inverse, pre-multiply this by T, and you get exponential of A. So that's the general approach that you can do, you can take to compute the matrix exponential. So you don't have to go through the Taylor series expansion of the matrix exponential in order to compute it. So this is sort of a simpler computational approach. You do need to know the eigenvectors of the matrix A. You do need to know the eigenvalues of the matrix A in order to do this. And most of the time you will be working with n equals to 5, 10, 15, in which case finding the eigenvalues and eigenvectors is not a big challenge. But if you are working with n equals to 1000 or 1 million, it becomes a problem. Okay. So for a 1000 cross 1000 dimensional matrix, finding the eigenvalues and eigenvectors is a very, very computationally demanding algorithm. But for a 10 cross 10, not quite. However, if you only have a 50-cent microprocessor, you probably won't be able to compute the matrix exponential on those microprocessors. So just keep in mind that whether you are able to compute this or not largely depends not just on the matrix itself, but also it depends on the computational device that you have to compute that exponential. So to give you an example, if you have a robot, humanoid robot, it has roughly 100 dimensional state space. So this A would be roughly 100 cross 100 if you're buying a modern humanoid robot. And if you were to compute the matrix exponential for that modern humanoid robot, you must have a GPU on the robot to be able to compute the matrix exponential. Otherwise, it will be very difficult. You won't be able to compute it in near real time. And so the humanoid robot will be very slow. Like this. It's not fun to work with slow robots, right? We want robots to be fast. Okay. Any questions so far? No? Perfect. So now let's look at the case for non-diagonalizable matrices. So how do we know if a matrix is non-diagonalizable? So let me write down the condition. In the previous lecture, we talked about algebraic multiplicity. Today, I'm going to talk about geometric multiplicity of a eigenvalue. So the next topic is non-diagonalizable A, Jordan canonical form. I don't know the history of Jordan canonical form, so unfortunately, maybe I should have read Wikipedia before I came to the class, but I did not. But I'm sure there is some history behind this Jordan canonical form. Okay, so let me remind you, I have a determinant of A minus lambda I. This gives me a polynomial in lambda. I set it equal to 0. Algebraic multiplicity well, before I talk about algebraic multiplicity, eigenspace and roots are lambda 1 to lambda n. Eigenspace Vi equals to the kernel of A minus lambda II. Algebraic multiplicity of lambda I equals to number of times lambda I appears in the set of eigenvalues. Geometric multiplicity of lambda equals to the dimension of the kernel space, dimension of Vi. So what the dimension of the kernel space of A minus lambda I is. And this stuff is from appendix A.6 of the book. So you can go and review it from that appendix. Generally speaking, these two need not be equal. Algebraic multiplicity of lambda I need not be equal to the geometric multiplicity of lambda I. If they are equal, then the matrix A is diagonalizable, if that is true for all lambda I. But if that's not true for all lambda I, then the matrix is not diagonalizable. Okay, so if these are equal for all lambda I, then algebraic multiplicity is equal to geometric multiplicity of for all lambda I, in which case for each lambda I you can find the same number of eigenvectors as its algebraic multiplicity. So you can find the same number of eigenvectors because kernel, the dimension of the kernel, is the same as the algebraic multiplicity. So you can compute n linearly independent eigenvectors, not n but ni, linearly independent eigenvectors, and you are done. Then you can start going through the diagonalization process. Now we are looking at a situation where this is not the case, where the geometric multiplicity is not equal to algebraic multiplicity. So let's look at an example. 2 1 0 2. This is my matrix. You will see matrix of this type in a critically damped mass spring damper system. Okay, if you are working on luxury vehicles, you want your suspension system to be critically damped, and you will spend considerable amount of time and effort behind building a suspension system that is critically damped or close to critically damped, in which case the eigenstructure of that particular system is going to look something like this. The matrix is going to look like this. Let's look at the eigenvalue. What is the eigenvalue of the matrix A? So let's do A minus lambda I determinant 2 minus lambda 1 0 2 minus lambda 2 minus lambda square equals to 0, lambda equals to 2 2. So algebraic multiplicity So the algebraic multiplicity here is equal to 2 because I have eigenvalue 2 which appears twice here. So the algebraic multiplicity is equal to 2. What about geometric multiplicity? So let's look at the kernel of A minus lambda I. This is V kernel of 0, 1, 0, 0 it's the set of vector v such that 0, 1, 0, 0 v1 v2 equals to 0, the set of vector v such that v2 equals to 0. In other words, v1 0. So v2 always has to be 0 in the kernel of this particular matrix. What is dimension of v? I'll let you guys write, think about it, and tell me what the dimension of v looks like. The dimension of the eigenspace corresponding to the eigenvalue 2. I have a matrix. I worked very hard to compute the eigenvalues of the matrix, and I figured out that the algebraic multiplicity of eigenvalue 2 is equal to 2 because 2 appears twice in the spectrum of this matrix. Then I want to look at the eigenspace of this particular matrix. So that's kernel of A minus lambda I. I substituted lambda equals to 2. I get kernel of 0, 1, 0, 0 matrix. That's given by the set of vectors V such that the matrix times the vector V is equal to 0. I did this math. Turns out this is V2 and 0. And that has to be equal to 0. So this means V2 should be equal to 0. This means that this set actually looks like V1 0. That's the entire set. So V1 can be any real number. What's the dimension of this particular set? 1. It's 1 because 1 0 lies in this particular thing, and then you cannot find any other linearly independent vector within this particular set. So the dimension of V is equal to 1, in which case the geometric multiplicity is equal to 1. So the algebraic multiplicity is not equal to the geometric multiplicity. Typically speaking, geometric multiplicity would be less than the algebraic multiplicity of the eigenvalue. Now the question is, if this is the case, then what do we do? Now I don't have a way to diagonalize the matrix. One of the requirements of diagonalization of matrix is that the geometric multiplicity must be the same as algebraic multiplicity for all eigenvalues. That's not the case here. Okay. So somebody, and I assume that somebody is Mr. Jordan, came up with this idea of generalized eigenvalue. And he said the following, that look, the kernel of A minus lambda I is single dimensional. So let's look at A minus lambda I square. What is A minus lambda I square? Can someone do the computation and tell me what this looks like? What about a minus lambda I cube? What is that equal to? It's also 0, 0. So something cool has happened. What is the cool thing here? The cool thing here is that as I keep increasing the exponent of this matrix, at some point of time, the rank of this matrix is equal to the rank of the matrix with the next exponent. So a minus lambda I square has the same rank as a minus lambda I cube. So he said, let's compute the following. We'll have an eigenvector v. We call it a generalized. Sorry, did I say generalized eigenvalue? No, I meant eigenvector. I'm so sorry. So he said, let's define this vector v. Let's call it 0, 1. So that a minus lambda I square v equals to 0. So let me call this v1, and v2 equals to a minus lambda I v1, and that is equal to 1, 0. Now v1 and v2 are linearly independent. Okay, so what did we do? We have this situation here where the kernel is one-dimensional. We need at least two independent vectors. Only then I can do some matrix operation. So how do I get the second linearly independent vector? So he came up with the idea. I think he went to sleep and he woke up in the morning and he had this idea that let's keep increasing the exponent of a minus lambda I and look at what the matrix looks like. And then he realized that at some point of time, the matrix rank is not changing. So I'm going to stop at the point where the matrix rank doesn't change if I increase the exponent. So he stopped at 2 because this is a two-dimensional matrix, 2 cross 2 matrix. And then he looked at a vector v1 such that a minus lambda I square v1 is equal to 0. And then he defined v2 as a minus lambda I v1. That gave the person v2. And turns out that v1 and v2 are linearly independent. And he called v1 and v2 as generalized eigenvector. And as is written in the appendix of the book, whenever you compute generalized eigenvectors corresponding to all the different eigenvalues that it might have, they are all going to be linearly independent. Okay, we are not going to prove that result in the class, and in fact the book also doesn't contain the proof of this result, but I'm pretty sure it might have referred to some other book for where this fact is proven. But essentially all the generalized eigenvectors corresponding to all the eigenvalues of the matrix would be linearly independent. As soon as things are linearly independent, I can construct a matrix T by stacking all those eigenvectors, generalized eigenvectors, and then I can do the same thing. At equals to T times lambda, where lambda will have some specific form. So I'll talk about that form. I have some time. and that is going to get me to the Jordan canonical form. So let me write it down. Can I erase this side of the board? Any questions so far? Okay. Okay. So I'm going to construct the matrix T as V1, Vn. These are all generalized eigenvectors of A, and it will turn out that AT equals to T times, you will have lambda 1, lambda 2, lambda k, and each of this lambda I would be lambda I, lambda I, lambda I, lambda I, 0 in the bottom triangular area, and then you will have 1, 1, 1, and so on, and then you will have 0 here. So right above the off diagonal term, you have 1 along the off diagonal entries, and then you have 0 everywhere else. So it has a very specific structure, and this is known as the Jordan canonical form. So if TikTok was around Jordan's time, he would be our hero. He would watch. He would be like the super influencer because he came up with this structure for the Jordan canonical form. Okay. So we did a lot of linear algebraic mumbo jumbo in order to get this Jordan canonical form. Jordan canonical form also has this diagonal structure. So you have along the diagonal, you have matrices, off diagonal, you have no matrices. Remember, our goal is to compute matrix exponential. So let's compute the matrix exponential. So I have T inverse AT lambda k. So T inverse exponential AT equals to exponential lambda 1 exponential lambda k 0 0. We are back to the square one, which is how do I compute the matrix exponential of this particular matrix? And as is always the case, I am going to write exponential of lambda I as exponential of lambda I plus ni, where ni is equal to 0 0 0 0 0 1 1 1 1 and then 0. So diagonals are all 0. Right above the off diagonal term, that one is equal to 1, and then all the other terms are equal to 0. Okay, so we did a lot of linear algebra for today. I'm going to pause, or rather stop here. We are about to about the closing time of this lecture. But I want to leave you at the cliffhanger, and the cliffhanger is, what's the matrix? So I know that these two matrices commute because we have done it in the past. Therefore, the exponential of this plus this is exponential of this multiplied by exponential of this. Now the goal is to compute exponential of ni. What is exponential of ni? So I want you to think about it, think hard, and then on Thursday we are going to meet at 4:35 ish p.m. So the class will not start at 3:55, but it will start a little late, and we are going to solve this mystery, which is what is exponential of ni. Okay, so thank you so much, and I'll be happy to answer any questions at the after this class is over. Thank you.